Here we're considering turning points, and this is actually part 2 of the turning point presentation. In this presentation we'll be calculating the maximum volume, the minimum surface area of various sections such as cylindrical sections and rectangular sections. And just note for reference, turning points are also referred to as stationary points, and I will use these terms interchangeably within this presentation. It is strongly encouraged that you've seen the previous presentation related to turning points before reviewing this presentation. There's a brief recap from the previous presentation. First I'll outline what turning points are in terms of the maximums and minimums, and the recap slide here, and also how to calculate the various maximums and minimums using the first differential and the second differential. It's essential that you understand this process for finding turning points, as this work will underpin the solutions we're about to review here. Here's another recap slide from the previous presentation. This slide shows the process for locating and distinguishing between stationary points. As shown here, essentially we have 4 steps in the process. In step 1 we were given the equation, function of x. We differentiated this to find the first differential. We equated it to 0, solved for the values of x, generally 1 or 2 values to find. We substitute the value of x into the original equation for y as a function of x to determine the associated value of the y-ordinate. This then locates the coordinate of the stationary point or points. Then we determine the second differential, d2y by dx squared, shown here, into which we substitute the x-ordinate determined, and from this we can determine whether we have a minimum, maximum, or even a point of inflection. Again, this process was shown in detail within the previous presentation. And again, an extract from previous presentations showing our standard derivative table, but in this particular presentation the only function we'll be considering is of the generic form ax to the n polynomial, and we have our standard derivative shown here, an x to the n minus 1. And here's a recap slide showing the quadratic formula that we may need to use, as sometimes the first differential is in the quadratic format, so we'll have to find 2 values of x. So it's assumed you're familiar with using the quadratic formula, as illustrated here. Here's a very brief introduction to the calculation of turning points related to practical problems. So there are many practical problems involving calculating the maximum and minimum which occur in science and engineering. Within such problems, usually an equation must be derived from the specified data given in the question and rearranged as required to contain only one variable. Typically that variable is x, but it can be any parameter that the question requires us to determine. The procedure on the following slide outlines a general approach that may be used within the solution of these problems. Introduction continued. So here's what's termed a general approach for determining turning points related to practical problems. Again, we have the 4 steps as outlined in the previous presentation for calculating turning points. The latter 3 steps in this process are the same as those we used in the previous presentation. It's just the first step that has been enhanced here. So within the first step now, unlike the previous questions where we were given a formula which we could then differentiate appropriately, this time with practical problems we have to actually generate the required equations from the parameters that are given in the question. These parameters might relate to dimensions, geometry. In this presentation often it will be area and volume. We then need to rearrange these equations to produce an equation with only one unknown. So later on within the presentation we'll be generating such equations as a is equal to a half pi d squared plus 4d to the negative 1. So that's surface area as a function of d. D is the variable we're trying to find, diameter of a cylinder. Also a volume formula here as a function of x. D is the variable we're trying to find, diameter of a cylinder. Also a volume formula here as a function of x. So that's just 2 examples of where equations are generated forming a function of only one unknown. We will then differentiate this equation with respect to the unknown variable so we will determine the first differential. As I said before, the rest of the steps shown here are the same as that we used in the previous presentation for calculating turning point locations and whether maximum or minimum. Well, we will solve practical turning point problems. Here's a very brief overview of the presentation. I'll first of all outline in detail example 2, where we have to determine the lengths of the sides of the square that ensures the volume is a maximum, and we've got to calculate what this maximum is. And also exercise 3, where we've got to determine the dimensions of an enclosed cylindrical section and calculate the minimum area associated with this section. These solutions will be worked through in detail for your reference. And here are the approximate start times related to example 2 and exercise 3. Please note these times are rounded to the nearest minute. We'll next review some tutorial questions from our workbook. As a continuation of the previous presentation, I will show the solutions to question 8, question 9 and question 10. And here are the approximate start times related to question 8 through to question 10. But again, please note these times are rounded to the nearest minute. But I will leave you with question 11 and question 12 extracted from our workbook to solve at your own pace. Example 2 extracted from our workbook. A small metal box is to be made from a rectangular sheet of metal having dimensions 0.36 meters by 0.24 meters. Dimensions shown here on the sketch relates to the length and the breadth of the box. 4 equal square corners are cut from the plate. Dimension x by x shown here for one of the corners. The sides, denoted as L and B, are folded to form the box. We have to determine the length of the sides of the square that ensures the volume is a maximum, and we're asked to calculate this maximum volume. Answers shown in the bracket here. So unlike in some of the previous questions of the previous presentation, where we were given an explicit formula and we differentiate appropriately to find the various turning points, here we generally have to derive the formula before we can actually apply the process for finding the turning points and if there are maximums or minimums. So within each question you have to consider the context given. In this particular question we have a rectangular box. We're asked to calculate the volume of the box, so we will need to consider the volume formula. So that's the initial part of the solution. We have dimensions of B, which is overall width shown here, which is 0.24 minus 2x. We also have the length of the box, L, shown here. Given the information in the question will be 0.36 minus 2x. And notice that they're both functions of x being the dimension of the corners to be cut out from the rectangular sheet. So now we can determine the volume of the box. From above it will be B multiplied by L multiplied by x. Here's example 2 continued, just showing a three-dimensional sketch of the box and the volume calculated from V is equal to BLX. Just clarifying the dimensions, B is 0.24 minus 2x, L is equal to 0.36 minus 2x. So we can now calculate the volume of the box in terms of x by inserting the B and the L into the formula BLX. So the volume of the box is stated as a function of x. All that's happened on the final line of the slide, I simply expanded these two brackets. There's a binomial expansion shown here. This expression can be simplified further, collecting like terms and multiplying throughout by x, which I'll show you on the next slide. Here's the bracket expansion using example 2 for the volume of the box, showing the binomial expansion here, collecting like terms here, then finally multiplying throughout by variable x to produce the volume formula as a function of x. Example 2, solution continued. Here's now the formula for the volume of the box from the previous slide. Let's produce this equation, which I've labelled as 1 for reference. Now we could actually solve this graphically from equation 1 by literally plotting a graph. So here's a plot of the volume V, meters cubed, against dimension x, showing the meters. This is the equation, volume that's been plotted. And we need to determine the value of x here on the horizontal axis, or where the maximum volume occurs, shown around here on the vertical axis. So it's that maximum turning point that we're trying to find in this particular case. So a graphical method is very useful, it's very visual, easy to understand, but it's not particularly accurate when trying to select the value of x and v. So we're going to use differentiation to calculate these values shown here of x and v. Back to our analytical solution. We know from our previous presentation to find the turning point we need to differentiate. So we have a volume equation in terms of x. So differentiating equation 1 to find the first differential dv by dx. In this case I'm using shorthand notation of v dash. From standard form, here is the first differential, called that equation 2 for reference. So that was the first step in our solution process. The second step now, equate equation 2 to 0 for a turning point. So the above equation is now equated to 0, and we solve the resulting equation. Note this is in the form of a quadratic, y is equal to ax squared plus bx plus c, turn the quadratic in x in this case, and we're going to solve this using the quadratic formula, shown here on the right hand side. Again, it's expected that you understand how to solve quadratic equations at this level of study. And just notice for reference, when reading the quadratic, the a associated with the x squared term is 12, it's positive 12. The b associated with the x term is negative 2.4, and the c, the constant in the equation, is 0.0864. So be very careful when extracting the a, b and c. The generic equation is shown as y is equal to ax squared plus bx plus c, but the equation we've derived, equation 2, is essentially in the form of c plus bx plus a squared. Solving the quadratic for x, there's always two solutions to a quadratic, but only one solution is valid in this particular case, and that's the 0.047 meters. Cannot use the 0.153 meters. It's an academic solution, because in this case we couldn't construct the box if the x dimension is 0.153, considering 0.153 doubled, so that value of x is not valid for this particular problem. So only 0.047 is a realistic dimension in the context of the question. Example 2, solution continued. Step 3 in our process is to actually find the volume at the turning point. So in other words, when x is equal to 0.047 meters, we simply use equation 1 derived on our previous slide, shown here at the top of the slide, and we insert the value of x of 0.047 into that equation. Evaluating the volume is 0.00183 meters cubed. So now we find the coordinate of the stationary point. There's only one stationary point in this solution, and we have our x value and our maximum volume value. Back to our graph here, we can see that 0.047 meters and the x 0.00183 meters cubed on the y seem reasonable in the sketch, and we can clearly see it's a maximum volume. But using differentiation, step 4, we find the maximum or minimum turning point by using the second differential. So now differentiate equation 2. That was our first differential shown at the top of the slide here. So the second differential, v double dash, or d2v divided by dx squared, shown here. Just call that equation 3 purely for reference. Inserting the value of x, where the maximum volume occurs, into equation 3. We find the second differential is a negative value. We're not interested in the actual magnitude of the second differential, it's just its sign, whether it's positive or negative. And as it's negative, then that means we have the maximum volume. And of course that's what the graph shows. The maximum volume occurs at x is equal to 0.047 meters. So that's the solution for example 2. Here's exercise 3. An enclosed cylindrical can, shown in the sketch on the right hand side, has to be made from thin sheet metal so that the surface area is a minimum for a volume of 1 meter cubed. we're asked to determine the dimensions and the minimum area, noting the surface area shown here for an enclosed cylindrical can and the volume formula shown here for a cylindrical can. The answers for diameter, height and surface area are shown here for your reference. If you think you can attempt this exercise without further assistance, well, I would encourage you to stop the presentation and do so, but I will show you the full work solution on the following slide. If you do want to attempt exercise 3 before reviewing the solution, here are the suggested steps in the process. Initially, rearrange the volume equation stated above for H, so that H is effectively a function of D. Notice the value of volume V is 1 cubic meter as stated in the question. Next, substitute the expression for H into the equation given above for the surface area of a totally enclosed cylindrical can. This then produces the area in terms of a function of D, the diameter. Next, we determine the first differential, as with dA by dd. We equate dA by dd to 0. We solve for the value of D. Then we back substitute the value of D into this equation to find the value of H. And finally, we determine the second differential, d2a by dd squared, to determine if we have a maximum or minimum turning point. So now I'd encourage you to stop the presentation and attempt exercise 3, but the full work solution is shown on the following slides. So exercise 3, commencement of the solution. Firstly, we generate the appropriate equations. Let's consider the equation for volume, as given in the question. Just slightly be arranged here. V is equal to a quarter multiplied by pi d squared h. Shown in the question is divided by 4, but I'm multiplying by a quarter here. Rearrange the equation for h. H is equal to 4v divided by pi d squared. Call that equation 1 for reference. Let's consider the equation for surface area, again given in the question. Slightly rearrange this. Instead of dividing by 4, I'm multiplying by a quarter again, but the same equation. Call that equation 2. And now we simply substitute equation 1 into equation 2 above. This is h inserted into equation 2. What's the formula for surface area in terms of D? Simply rearranging the second term on the right hand side on the next line. We've got pi divided by pi, so that cancels, and d divided by d squared, so that's divided by d here. And just note in the question that the volume V in this case is 1 meter cubed. So substituting 1 for the V, the area is equal to this expression. So area is now a function of D. Exercise 3, solution continued. Here's a more detailed slide purely for reference, showing how we inserted our expression for H, shown here of 4v divided by pi d squared, into our surface area formula, A here. Just note 2 multiplied by a quarter, with a quarter shown here, is equal to a half, where the half is derived from here. So inserting for H, the 4v divided by pi d squared. Notice how the pi in the numerator here cancels with pi in the denominator, and also how d in the numerator cancels the squared term in the denominator, leave us purely with d in the denominator. So that simplifies to 4v divided by d. On the following line, I simply brought d from the denominator, the bottom line, into the numerator, the top line, and made it d to the negative 1. The question states that the actual volume V in this particular case is 1 meter cubed, so I can simplify the expression here to 4d to the negative 1. So if you're slightly struggling with the transposition, hopefully this slide will enlighten you in that regard. Call that equation 3 purely for reference. Exercise 3, solution continued. Now differentiating the area equation with respect to diameter d. Let's find the first differential, dA by dd, shown here using standard forms, referred to as equation 4 for reference. Next we equate the equation to 0 to find the turning point, so 0 on the left hand side, dA by dd, equals to the right hand side. To solve this equation for d, we're going to multiply throughout by d squared. So multiplying both left and right hand sides by d squared, we have 0 is equal to pi d cubed minus 4. Next, going to rearrange for d. So in other words, add 4 to both sides, divide by pi, and cube root both sides, making sure that d is equal to 4 divided by pi, or cube rooted, so power of a third there. So d is equal to 1.08385 meters. If we now back substitute the value of d to equation 1 on our previous slide, that's this equation here, we can find the value of h. H is equal to 4 divided by the pi d squared, so that is our d value from above. So h is the same numerical value as d in this case. To find the surface area A, when d is equal to 1.08385 meters, we use the equation for area from the previous slide, equation 3 shown on this slide. And we insert the value of d appropriately within the equation, and that solves for an area of 5.536 meters squared. So we now have a turning point location when x is equal to 1.084, that's a d value. The y value, or the volume, is 5.536, to 4 significant figures. Exercise 3, solution continued. Just repeated equation 4 here on the right hand side for the first differential of dA by dd, purely for ease of reference. So now in step 3 here we're going to check for the minimum area, differentiate equation 4 above, form d2a by dd squared. So differentiating pi d with respect to d becomes simply pi, and differentiating the minus 4d to negative 2 becomes positive 8d to negative 3. What we note now is the second differential is positive. In other words, if we put the value of d from the previous slide, shown here, into our d2a by dd squared equation, the right hand side will be a positive value, so this stationary point is a minimum. Exercise 3, solution continued. Here's a plot of the equation for surface area, equation 3 shown on this slide, and a minimum value appears to occur here on the curve where the diameter is 1.084 meters, diameter shown on the horizontal axis, reading on the horizontal axis, and the area in meters squared on the vertical axis is 5.536, so reading horizontally across in this location. So we can clearly see this turning point is a minimum. I've just shown another way of calculating the minimum using this alternative approach, but I suggest to use the second differential as shown in step 3, finding the type of turning point. Here's question 8, extracted from our workbook. The total surface area of a rectangular block having height h with a square base of side x centimeters is 600 centimeters squared. We've got to show that the volume of the block is equal to a half multiplied by, in the bracket, 300x minus x cubed. That volume is in centimeters cubed. We've also got to determine the maximum volume of the block. Answer is shown here in the bracket. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so. For your reference, I will outline the solution on the following slide before showing you the full detailed work solution. Here's question 8, showing suggested solution steps. Solving the problem. Initially, we need to form an equation for the total surface area, with A here, and this needs to be a function of both x and h. Next, we need to rearrange the equation for A for h. I'll label this equation for h1, purely for reference. Next, we need to generate an equation for volume, V, and this again is a function of both x and h. Call this equation 2. We need to then substitute equation 1 above into equation 2 to find the volume, but this time purely as a function of x. Label equation 3 for reference. We then need to determine the first differential, dv by dx. We need to equate dv by dx to 0, solve the resulting equation for x. Then we need to back substitute the value of x into equation 3 above to find the volume. And finally determine the second differential, d2v by dx squared, to find if this is a maximum or minimum volume. So again, if you think you can solve question 8 on your own, I would encourage you to stop the presentation and attempt the solution, but the full detailed solution is shown on the following slides. And I also suggest you always draw sketches of the problem where possible. So here's a diagram of the rectangular block having the square base x by x and height h. Here's question 8, full work solution. I'll let you review this at your own pace. Just note from the question, the surface area of the rectangular block is 600 centimeters squared, so symbol A, 600 centimeters squared. And as our formula for surface area, 600 is equal to 2x squared plus 4xh. 2x squared would be the top and bottom, and the 4xh term is the area of the four sides, as indicated in the sketch on the right hand side here. Next we're going to rearrange this surface area equation for h by first of all subtracting 2x squared from both sides of the equation, dividing throughout by 4x, writing this in terms of partial fractions, and then simplifying. H is equal to this expression, which we've referred to as equation 1 for reference. We form an equation for volume in terms of x in h, equation 2 here, and then we substitute equation 1 into 2 to find the volume purely as a function of x. We simply expanded the bracket to find volume in this form, but note it can also be expressed in this factorized form here, which is the same as that given in the question which we're asked to show. Here's question 8, solution continued. So just recapping from the previous slide, volume, call that equation 3 for reference. We differentiate equation 3, get v dash here, dv by dx in other words, shown here. Standard form, ax to the n, call that equation 4. We now equate to 0 for a turning point, so 0 is equal to the expression, and we can rearrange to find the value of x, basically adding 1.5 x squared to both sides of the equation, dividing by 1.5 and then square rooting. X is 10 centimeters. Then from equation 3 above, we can find the volume when x is equal to 10. So inserting the value of 10 into equation 3, we find that the volume is equal to 1000 centimeters cubed. So now we have our stationary point. Here is at 10 centimeters. That will be on the horizontal axis if plotted. And the volume of 1000 centimeters cubed would be on the vertical axis. And finally, to determine the maximum or minimum, we're going to use the second differential. So differentiating equation 4 above, we get our second differential v double dash, d2v by dx squared in this case. That gives us negative 3x. For our stationary point, x is equal to 10, so we can see that's a negative value from the second differential. So negative value relates to a maximum. Question 8, solution continued. And here's the graphical solution to question 8. We plotted the volume formula given in the question. And we can see we have a maximum turning point, x equal to 10 meters, gives a maximum volume of 1000 meters cubed. Maximum turning point labelled here. That's the solution to question 8. Here's question 9 for your reference. A square sheet of metal, edge 1 meter, has a side x meters cut out of each corner, and the remainder of the sheet is folded to form an open box. We've got to prove that the volume of the box is, given by this expression here, and we've got to find the maximum volume of the box. The answer shown here in the bracket, 2 divided by 27 meters cubed. I think you can attempt this question without further assistance. I'd encourage you to stop the presentation and do so now, but I will show some further hints on the following slide. Here's a suggested outline of the solution, showing suggested steps. I'll let you review these at your own pace. Again, I've drawn a little sketch of the problem on the right hand side. So now I'd encourage you to stop the presentation, try and follow the steps, but the full work solution is shown on the following slides. So here's question 9, beginning of the solution. I'll let you review this solution at your own pace. Note the volume of the box asked to be proved in the question is shown here within the solution. Solution continued. Again, we have a formula for volume, as a function of x here, equation 1. Differentiate it, find the first differential, equation 2. Note when you equate equation 2 to 0 this time, you have to solve a quadratic problem, but only one of the solutions will be valid. And question 9, solution continued. Here we find the maximum volume, doing both fraction and decimal. I have laboured the use of fractions here for your reference. Some students find fractions difficult to follow. I tried to labour the solution to help you here. And as always, we have to finish by finding if it's a maximum or minimum turning point using the second differential. We find that for an x value of 1 upon 6, the volume is a maximum. Question 9 continued. Here's the graphical solution. There's the maximum turning point location, given in fraction form and also in decimal form, so 4 decimal places. And of course the minimum turning point is shown here, but that's not a valid solution in this case because that cannot form a box. Here's question 10 from our workbook. If the volume of a circular block is equal to 750 centimeters cubed, we've got to show that the total surface area is given by this equation here, or x centimeters is the radius of the base. Then we've got to obtain the value of x, which makes the surface area a minimum, and we've got to calculate that surface area. So here's the value of x, and here's the area. I encourage you to stop the presentation and attempt question 10, but I'll show you the full work solution on the following slides. So here's question 10, beginning of the solution. I'll let you review this at your own pace. Just note again, we were given a formula in the question to prove, and we've done so here, formula for the surface area of the circular block. Question 10, solution continued. Our formula for area from the previous slide. Differentiate it with respect to x, equate to 0, solve for x, this time it's a direct solution, and then knowing the value of x, we can determine the area of the section, area shown here to 3 significant figures, and we can also find if it's a maximum or minimum using the second differential, more standard form here to find the second differential, and we can clearly see if x is equal to 4.924 centimeters, inserting that into equation 3, we will have a positive value, so this must be a minimum surface area. Question 10 is the graphical solution. We show here our turning point or stationary point. It's a minimum in this case and occurs at this location in the x and in the y, which is the volume in this case. I will leave you with question 11 and question 12 extracted from our workbook to solve at your own pace. Answer to question 11 shown here. Answer to question 12, which is in 2 parts, shown here. Here's the bibliography used to help generate this presentation, which I hope has been of some use to you, and as always, thank you for viewing.